I will try to get started here. Let me we begin with a word of prayer. So, Heavenly Father, we thank you for this day again. I thank you for this class and this time we have to meet and study your creation. Just pray that you would guide our steps this morning and help us to understand a little bit more about how the column correspondence property works and all that, Lord. In your name I pray, Lord Jesus. Amen. Before I get started, I have a verse for today. Do you guys know why jogging is evil? I would cite Proverbs 28:1 for you. Proverbs 28:1 says the following. It says, "The wicked flee when no one is pursuing, but the righteous are bold as a lion." So think upon this verse before you exercise in that way. I shall begin. So we talked about elementary, that was a joke, elementary matrices, just to be clear. I was raised by a mother who, every time we saw our neighbor jogging, she would stop the car, roll down the windows and ask him if he needed a ride. Full context, these are not power windows. You have to lean across and do this. It takes like a solid 5 seconds, so. All right, so if we were to say take, let's say 1, 2, 3, 4, 5, 6, X, Y, Z, just for fun. This is a 3x3 matrix, and I was to hit it with, say, let's see here, 1, 0, 0, 1, 1, 0, 0, 0, 1. What does it do? All right, so what we get is 1, and then here 1 plus 4, and then X, and then we get 2, we get 3. In the middle one I get 2 plus 5. I get 3 plus 6 over here. Y, Z. Right? 1, 2, 3, 5, 7, 9, X, Y, Z. So if I call this thing here A, all right, that matrix A, then what is this? If you'll allow me this short manga style calculation, we're looking at, row 2 getting replaced by row 1 plus row 2, right? Row 2 is getting replaced by row 1 plus row 2. So this matrix, oh my bad. It's 8:15, I'm going to do that kind of thing. Just stop me before I go too far. So this is A, I'm multiplying this by E. This is an example of a elementary matrix. Now this elementary matrix, we could denote like this. It's basically I, such that we're taking, row 2 plus row 1, and we're putting it into row 2, all right? Let me do that explicitly here. So I start with 1, 0, 0, 0, 1, 0, 0, 0, 1. I do the row operation, row 2 plus row 1, row 2 plus row 1, and that gets me to, all right, and that's the E I just talked about. So there's a theorem that we can observe here, and the theorem is simply this. Given any elementary row operation, let's just call it R for just sake of discussion. If we take, the identity matrix and do R to it, right? In other words, if we take, so let me say what I mean in words by this. What I'm saying is take, the identity matrix and perform row operation R, right? Then EA is the matrix obtained by doing R to A. So in other words, my example 1 up here, it's not a one-off, it's not an accident. I don't have to qualify when does this happen. This is in fact a general pattern. If I do a row operation to the identity matrix, if I left multiply by that same matrix on an appropriately sized matrix A, that does that row operation. All right? So what does this mean then? So, the theorem that follows given A in Rm by n, there exist elementary matrices E1, E2, Ek, right? Such that what? Well, Ek times Ek minus 1, E3 times E2 times E1 acting on A give me what? What can I do with elementary row operations if I do enough of them? And I follow the Gauss-Jordan elimination, right? Do the forward pass, do the backwards pass. We can get to our beloved reduced to echelon form of A, right? So now if I do this, what size matrices are these elementary matrices I'm talking about here? A is what? M by n. So I'm left multiplying these elementary matrices. Elementary matrices are square, right? How big are these ones? What was that, an n or an m I heard? N? Nope. Nope. The answer is m. Did you say m? We need to pick different letters, but it is what it is. So m by m, as in mommy, by mommy. All right. Because I have to have I have to have this, so I'm doing m by m, right? A is m by n, we're stuck with that. So these m's have to match in order to make that multiplication make sense, right? If you missed the last class, if you see the very end of it, you can see what happens when you try to not do that, okay? Like it doesn't work. Okay, so, I mean, this is interesting perhaps. Now let me jump the gun a little bit here and show you, I need to give you a definition because there's something I need to derive right quick here. So one of the things that's interesting about, there's many different things that are interesting about matrices, but one important thing, of course, is that they don't commute, right? In other words, A times B is not equal to B times A usually, generally speaking. Even if you can form the multiplication, even if the matrices are the right size to multiply, there's no guarantee that A times B is B times A, right? The other thing that's a little bit weird is you can have a non-zero matrix, right? And it doesn't have to have an inverse. So what's an inverse matrix? We say A in Rn by n is invertible, right? If there exists B in Rn by n such that AB is equal to I and BA is equal to I. In this case, we say B is equal to A inverse, all right? So we don't write 1 over A. That is not a notation that we use, all right? So 1 over A is a notation that we reserve for things like numbers, all right? A inverse helps us not to assume commutativity of multiplication for matrices. But this is what it means for a matrix to be invertible, all right? So this is one of our goals this week, is to understand the problem of finding a matrix inverse. And so I guess I can give you an elementary example. If we have the 2 by 2 matrix, A, B, C, D, right, the inverse of that is actually given by 1 over AD minus BC. You flip the diagonals, put minuses on the off diagonals, provided what? Well, we certainly need that AD minus BC is not equal to 0, right? So some of you already discovered that that is a necessary condition, right, for a 2 by 2 system with arbitrary coefficients to have solutions for no matter what the inhomogeneous term is. That was a problem in mission 1, right? You maybe recognize this condition. Now, you can believe me or not, but we can quickly check if this formula is right? So how do we check? So we take, you know, I'll put the inverse on this side. So I got 1 over AD minus BC. My alleged formula, A minus B minus C A. And we just have to multiply by A, B, C, D, see what happens, right? So my first multiplication is dA minus BC. Next up I get minus AC plus AC from this and that. In the 1, 2 spot I get dB minus BD. And finally in the 2, 2 spot I get minus CB plus AD. But if you look at that, what do we have? We have the identity matrix, right? The 2 by 2 identity matrix. Because these cancel, right? Chunk, chunk. And this is the same as that, right? So I bring that in, and I get 1 in both spots. So what this calculation shows you is that my, ABCD inverse times ABCD is equal to the identity matrix. And so likewise, you can show that ABCD times 1 over AD minus BC, flip the diagonals. Let's see here, dA minus B minus C is equal to 1, 0, 0, 1. So indeed, this proves that my formula is correct, right? Now you can wonder, where on earth did this formula come from, right? And I certainly have not explained, I just pulled it from the air, right? But there is a method to derive this formula we'll find after test 1, so I'll leave it for there. But now that we know that this is the 2 by 2 inverse, we can solve any 2 by 2 matrix problem with this, right? Like, let's do that right quick. So example 3, you know, if I'm going to solve 3x minus y equals to 10 and minus x plus 8y equals to alpha, well, then this is the way to do it. So what you got is 3 minus 1 minus 1, 8, xy equals to 10 alpha. So if I multiply this by the inverse matrix, so let me rewrite this for a second. This is A, this is V, this is B. So if you have AV equals to B, that says that A inverse AV is A inverse B. I can multiply both sides on the left by the inverse of A, all right? And so that gives, so what is A inverse? Well, that's IV, right? But what is I? Remember, identity matrix times anything just gives you back the anything, right? So that gives me V is A inverse B. But let's actually work that out. In other words, XY is equal to A inverse. What is A inverse here, though? We do what? A times D, which is 3 times 8, 24, minus what? Yeah, 24 minus 1, right? And we flip the diagonals. Minus is on the off diagonals. Multiply by my inhomogeneous term, my B, which is 10 alpha. And what do I get? I get, you know, 1 over 23, 80 plus alpha, 10 plus 3 alpha. Or if you like, 80 plus alpha over 23, comma, 10 plus 3 alpha over 23, right? I don't think it's an exaggeration to say that that takes like 50% less time than the other method for most people in here. And the likelihood that you make a mistake doing the algebra for like a substitution on a symbolic problem like this, the likelihood is high, right? But this inverse matrix multiplication method is super nice. If you have the inverse matrix, to a given coefficient matrix, that essentially unlocks the key to solve the system for arbitrary inhomogeneous terms. Now, can we always do this? Well, no. We can't always do this, right? And I'm never going to teach you a formula for a 3 by 3 matrix, the inverse for a 3 by 3 matrix, right? It's somewhere in my notes, there is that formula. But no one should memorize that. You'd have to be a truly ridiculous student to memorize that 3 by 3 inverse formula. I've had such a student. Did I talk to you guys about min yet? It was min. But anyway. All right, so we'll come back to the calculation of inverse matrices later this week, but I just need to introduce the concept because I want to point out something to you, which is that elementary matrices are invertible. So, by the opposite of the row operation, that defines it. So, like, some of these are really, really simple. Like, what's the inverse of a row swap? So laptops need to be put away during class. So thanks, guys. So the opposite of a row, what do you say?
Just kind of like put it in the back.
Yeah. So the inverse of a, goodness gracious, I lost my stuff. Oh, here it is. So the inverse of a row swap is exactly the same row swap. So like, for example, if I had row I swap with row j, the inverse to that is itself, right? Another example, if I had E of row I plus A row j goes to row I, want to calculate the inverse to that row operation, then you could just do I is row I minus A row j goes to row I. Listen, I don't really want to get into the details of what I'm saying here at the moment, because I have more to tell you today than if I dive into details here, we'll not get where we need to go. But I would like, if you could just trust me for today, that any elementary matrix is in fact invertible, and its inverse is actually essentially a row operation, the elementary matrix which comes from a row operation of the same type. So this is another theorem we have. But there's more. The next theorem that I'll share with you guys is the sock shoes. So sock shoes says that AB inverse is equal to B inverse A inverse, provided A and B in R n by n are invertible. So this is reminiscent of the similar formula for the what? For the transposition, right? The proof of this is really short. Check it out. So if I have AB times B inverse A inverse, what happens? And if I have B inverse A inverse times AB, what happens? See, I have A times, what's BB inverse? Well, that's the identity matrix, right? And if I have AA inverse, what's that? That's the identity matrix, right? But then I'm left with AA inverse and B inverse B, and what are those by definition? Again, by definition of inverse, those are the identity matrix, right? So you put these two things together, and we see that the inverse to AB is given by B inverse A inverse. So to calculate the inverse of a product, we multiply the product of the inverses in opposite order. This matters because matrix multiplication is not necessarily commutative. The order of multiplication matters. By the way, there are other things that work like this, like function composition. If you calculate the inverse of a composition of two functions, it also satisfies this rule. Like the inverse of f composed with g is g inverse composed with f inverse. But it's not something we emphasize a whole lot in like pre-calculus or anything, so if you don't know that already, it's not a big deal. Okay, so if you can do it for 2, you can do it for k, right? So if you extend this theorem, so extended, right? Socks, 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 shoes theorem. Sorry, I'm an idiot. So if you had like A1, A2, AK inverse, what would that be? That would be AK inverse, A2 inverse, A1 inverse. So whenever you're inverting a product, it's the product of the inverses in opposite order. So the point I have to all this is that if we have a product of elementary matrices, right, each of which is invertible, I have the following lovely formula, which is that if I let E equal to EK times EK minus 1 all the way down to E2 times E1, right? If I just let E be the product of all the elementary matrices, is E invertible? Well, I'm just telling you, the theory of inverse matrices is, in fact, that the product of invertible matrices is invertible. In fact, we could prove something stronger for elementary matrices. We could prove that the product of elementary matrices, well, I'll shut up. But so this inverse is what? This is E inverse is what? Is it invertible? It is, because each one of these is invertible, and the inverse is E1 inverse, E2 inverse, dot, 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 E, K minus 1 inverse, EK inverse. All right, so the product of elementary matrices is invertible, like that. And by the way, each one of these, let's say it this way, EJ inverse is an elementary matrix also. I got K of them. All right. Okay. So, trying to do the weave this morning. I'm not sure I'm awake enough to do the weave, but I'm awake. But so, like, if you look at the course planner, you'll notice that I say we're in chapter 4 today. Right? What's between chapters 2 and chapters 4? Well, there's chapter 3, right? So chapter 3 we'll come back and cover later. Chapter 3 is actually on what are called determinants. So like test 1 doesn't have determinants on it. Some of you have used determinants in the homework, which is lovely, but you can't do that. We don't know those yet. I mean, the internet knows about them for sure, and I do appreciate, when you guys do research on the homework, you can try to find answers to my homeworks online. I'm not saying you can't. I'm just saying that when you do, you have to understand the context of this class, which is you can't use a solution that's from like the middle of the course at the beginning of the course. We haven't, we don't have the life experience to say those words yet. So, however you want to look at it. But more to the point, I want you to be able to solve the homework in the way I solve it. So make sure you look at the solution before you're done studying, okay? All right, so we now have a bunch of toys that we can play with, in particular elementary matrices, which are, by the way, invertible, okay? So we can use these things to understand the following questions. There's 2 questions we need to look at. So there's 2 big ideas. And these are real big ideas. They'll be with us for the rest of the course. All right? So the one is span. So if we take the span of, let's say, V1, V2, let's say VK, right? This is equal to the set C1, V1 plus C2, V2, CK, VK, such that CJ is in the reals for all j. In other words, you could write it like this. It's the sum j equals 1 to k of CJ, VJ, right? Such that CJ are real. So let me put it into words. The span is the set of all finite linear combinations. It's the set of all linear combinations of these vectors. So this is the set. So if I call this thing S, all right? So S is, all linear combinations of vectors from S. In fact, I'm sorry, I've messed it up a little bit. So this is just the span of a finite list, right? But you know, if I had an arbitrary set like this, if I had the span of, let's say, W, all right, what this would be is like the sum j equals 1 to, you know, j equals 1 to k of cj, wj, such that the cj are real numbers and your wj's are in w. So the set you're forming the span of, it doesn't just have to be a finite list. It could be infinite in extent, and you can still talk about its span. But if you do this, the understanding is you just look at all possible linear combinations from this set, right? So this is a span. And corresponding to this, we say S is a linearly dependent set if we can remove some vector, we can remove some vector in S and have the span of S with the vector removed equal to the span of S. So I don't personally like this. I mean, this definition's intuitively helpful, perhaps. Like it says that, perhaps a better way to say this, logically equivalently, if V naught is equal to a sum, j equals 1 to k of cj vj for vj in S. All right. Then S is linearly dependent. In other words, you can take one vector in the set and build it as a linear combination of other vectors in the set. That makes it a linearly dependent set. Just to give you an example before I get too far afield here. So let's see here, like, what example am I on? 4? 3? Where am I? You just have to remind me. I lost track of my numbers. 3, thank you. So if I have the set 1, 2, 0, 1, 1, 3 is linearly dependent, since if we take 1, 2 plus 0, 1, what do we get? 1, 3, right? And it turns out if we study this, we're going to be able to argue, I probably will argue this in a future class, that means that the span doesn't change. If we were to look at the span of all three vectors, right, that would be the same as if I looked at the span of just the first two. All right. So this is one thing, the concept of a span, which is to say all linear combinations of a given set of vectors. But that quickly leads us to start talking about, well, what's linearly dependent? What's that mean, right? So that's the second big idea is S is, let's say S equal to V1 Vk is linearly independent, which we thankfully have an abbreviation for, namely Li, if and only if C1V1 plus C2V2 plus CKVK equals to 0 implies C1 equal to 0, C2 equals to 0, CK equals to 0. That you could take that as the definition of linear independence. I often do. It is logically reasonable to say, well, that just means that the set is not linearly dependent. That's also logically true. But this is just a good thing to memorize. This linearly independent, a set linearly independent, means that if you take a linear combination of those vectors equal to 0, it forces it to in fact be the trivial combination. This ensures actually that not one of those vectors can be written as a linear combination of the other ones. This is an elegant way of capturing the concept that there is no linear dependence amongst the vectors here, v1 through vk. All right. Now, at this point, you might wonder what on earth any of this has to do with what I started class with, right? You know? Like, so why were you talking about elementary matrices at the start? How does that help us? Well, I'd like to show you. Uh-oh. It's all right, people at home. I never moved to the middle board. Yowzers. Any questions while I'm letting it sit here for a second? All right, so one of the fundamental questions that we'd like to answer going forward, I mean, there's two basic questions that related to these two big ideas. So the problems that we'd like to solve, I can't spell solve, that's not a good sign. One is W an element of the span of V1, V2, Vk? Like, that's one question. Another question is V1, V2, Vk linearly independent, subset? So by the way, everything I've talked about is all in Rn, right? These definitions actually are still, we can make these definitions in abstract vector space, but we keep it real in here. We're focusing on column vectors, so we'll do that. So let's see here. So example 4. We can ask the question like, is 1, 2, 2, 0 in the span of, let's say, 1, 0, 0, 0, 0, 1, 1, 0, and you know, I don't know. 1, 1, 1, 1, for instance. So there's a decent question that we can ask. So what are we asking? We're asking, can you find C1 times the 1, 0, 0, 0 vector plus C2 times the 0, 1, 1, 0 vector plus C3 times the 1, 1, 1, 1 vector such that we get back 1, 2, 2, 0. Can we solve this system? All right. Well, let's write it in the notation that we are, more adept at working with, which is what? Like matrix times a column vector, right? So this is the same as what? 1, 0, 1, 0, 1, 1, 0, 1, 1, 0, 0, 1 times what? C1, C2, C3 equals to 1, 2, 2, 0. All right, so you guys help me out here. Help me out with the row operations. Here we got 1, 0, 1, 0, 1, 1, 0, 1, 1, 0, 0, 1. And our inhomogeneous column is 1, 2, 2, 0. What are we going to do here? How about we'll do row 1, row 2, row 3 rather, minus row 2, right? Which gives us what? 0, a 0, a 0, a 0, and then we've got 0, 0, 1, 0, right? And this is a notation we can use if we see what's going to happen, but we don't want to write out the steps, if there's no danger. So like what happens here? You're going to do what? You're going to clear out above that 1, right? So we're going to get ourselves to 1, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0. I'm going to put the 1 up here eventually, right? And let's see here. I still have the 1. I still have this 2. Nothing happens to that 2. I still got the 0 here like that, right? So what does this tell me? This tells me that C1 is equal to 1, C2 is equal to 2, right? And C3 is equal to what? 0. Which makes total sense, right? Because if you go back and look at my purple equation, you can easily see that what? If I put a 1 here, right? If I put a 1 here, a 2 here, right? If I put a 0 here, we get that, right? So what's the answer to my question? Yeah, apparently, let me give these names. Let's call this V1, V2, V3, right? So 1, 2, 2, 0 is equal to V1 plus 2, V2, which is, of course, in the span of V1, V2, V3. All right, so then what? I want to point out something to you. Look at the reduced row echelon form of the matrix, right? See this here? This guy and that guy. What can you see? 1, 2, 0, 0 is equal to what? It's kind of dumb, but it's 1 times the first pivot column plus 2 times what? Right. What's true over here? I mean, it's kind of a dumb example because they're so much the same, but notice here the same pattern holds, right? This is actually not an accident. This is a general theorem. Let me write the theorem down. Any linear dependence amongst the columns of A is also found amongst the columns of the reduced row echelon form of A. This is what I usually refer to as the CCP, the column correspondence property. So how do you prove such a thing? Well, the answer is with elementary matrices. So if I think I can show you. Actually, I think I'm not going to hurry the proof today. I'll do the proof at the start of next class. I want to show you one more example of this. Maybe a little bit bigger example. So I'll use the matrix calculator website. We will make up a big old matrix. Let's say 4 rows and 7 columns. All right. If I can get this plugged in. So you guys don't have to worry about writing this down. Once we're done with class, I'll print this page as a PDF and post it in an announcement, okay? So you don't have to fuss about writing this down, all right? But I want us to all appreciate what's going on here. So let's take the first column and make it something kind of funny, like 1, 3, 5, 7. We'll make the second column something relatively easy, 0, 1, 1, 0. We'll make the third column the first two added together. So what's 1 plus 0 is what? 4. You guys help me out here. 6, 7. We'll make the fourth column the difference of the first two columns. So 1 minus 0, 3 minus 1 is 2, 5 minus 1 is 4, 7 minus 0 is 7, We'll make the fifth column something new, like 4, 3, 2, 1. We'll make this one 1, 1. I'm just filling out these. I don't know what these are. And this one, I'll make 2, 6, 10, and 14. Let's see what happens. So remember, how did we form the third column? It was the sum of the first two, right? And the fourth was the difference of the first two. See what happens down here? We've got sum of the first two. This is the first one minus the second one. This one, something new. We can't form this column, this fifth column, as a linear combination of any of these because I just made something up which wasn't just a linear combination of the first two pivot columns. This guy over here, as it happens, is 1/9 that plus 2/9 that. In other words, this 1, 2, 3, 4, 5, sixth column you can build as a linear combination of this one and that one. And then the last one is 2, 0, 0, 0. Why is that? What is the last column in my example? How did I make it up? See this? I just twice the first column to get the last one. And that is echoed down here in this. See, twice that. So the point of all this is that the reduced row echelon form, it is very simple to see any kind of linear dependence in the reduced row echelon form. So what is hidden in the original matrix is revealed in the reduced row echelon form. Anyway, more examples of this next time. I'll shut up.